I hope you're doing great. Thank you so much for your support and for being part of this course. Now let's solve another important electric field problem. In this example, we have a uniformly charged ring, and we want to find the electric field at a point located on the axis of the ring. We'll solve it step by step using symmetry and integration. Step 1. If we look at the figure, we first choose a very small charge element on the ring. We call this element dq, and its small arc length is ds. Since the charge is uniformly distributed, dq equals lambda times ds. Also, remember that the linear charge density is lambda equals q divided by 2 pi r. Here, 2 pi r is simply the circumference of the ring. Step 2. In this step, we calculate the electric field produced by this tiny charge element using the same electric field equation for a point charge. First, we find the distance from the element to point P. Using the Pythagorean theorem, R equals the square root of z squared plus r squared. Now we apply Coulomb's law. dE equals k dq divided by r squared. Substituting dq equals lambda ds, we obtain dE equals k lambda ds divided by z squared plus r squared. Now let's continue by resolving the electric field into its components. Step 3. If we look at the second figure, we can see something very important. Every charge element has another element directly opposite it on the ring. The horizontal components of their electric fields have equal magnitudes but opposite directions, so they cancel each other completely. Only the components along the z-axis remain and add together. Using the geometry of the triangle, cosine theta equals z divided by r. Therefore, DEZ equals DE times cosine theta, which becomes k lambda z divided by the quantity z squared plus r squared raised to the power 3/2 times ds. Step 4. Now we integrate these remaining components around the entire ring. Since all the terms are constant except ds, we move the constants outside the integral. The integral of ds over the whole ring is simply the circumference, which is 2 pi r. Finally, we substitute lambda equals q divided by 2 pi r and obtain the electric field of a uniformly charged ring, E equals kqz divided by the quantity z squared plus r squared raised to the power 3/2. Step 5. Finally, let's consider a point very far from the ring. When z is much greater than r, we can neglect r squared compared with z squared. This simplifies the equation to E equals kq divided by z squared. This means that at large distances, the charged ring behaves just like a single point charge, with total charge Q. This is a very important result to remember because it appears frequently in physics exams. Let's continue with the next example. In this example, we're going to calculate the electric field produced by a uniformly charged circular disk. The good news is that we don't have to start from scratch. We'll use the electric field formula we derived for a charged ring in the previous example. If we look at the figure, instead of treating the disk as one solid object, we divide it into many thin concentric rings. Each ring has a radius r and a very small thickness dr. Step 1. Define the charge element. The area of one thin ring is simply its circumference multiplied by its thickness. Since the circumference of a circle is 2 pi r, the area becomes 2 pi r dr. Now multiply this area by the surface charge density, sigma. That gives the charge of one ring. dq equals sigma times 2 pi r dr. Step 2. Electric field of one ring. Now we calculate the electric field produced by this small ring. Instead of deriving a new equation, we directly use the electric field formula for a charged ring that we proved in the previous lesson. Then we substitute the expression for dq into that formula. After simplifying, we obtain the differential electric field ready for integration. Step 3. Integrate over the whole disk. Finally, we add the contribution of every ring by integrating from the center of the disk, where r equals 0, all the way to the edge, where r equals capital R. To solve the integral, we use the substitution x equals z squared plus r squared. After integration and simplification, we obtain the electric field of a uniformly charged disk. E equals sigma over 2 epsilon 0 multiplied by, open parentheses, 1 minus z over the square root of z squared plus r squared, close parentheses. This is a very important result, and I highly recommend memorizing it. You'll use it again and again in Physics 2 and many exam problems. If the radius becomes infinitely large, the disk behaves like an infinite charged sheet, and the electric field becomes E equals sigma over 2 epsilon 0. This result is extremely common in exams, so make sure you remember it. We've reached the end of Chapter 2. Before moving on to the next chapter, let's quickly review the most important concepts and formulas from this chapter. First, remember the definition of the electric field. The electric field is the force acting on a positive test charge divided by the value of that test charge. Next, for a point charge, the electric field is proportional to the charge and inversely proportional to the square of the distance. For an electric dipole, the field decreases even faster with the cube of the distance. Then, we studied the electric field produced by a uniformly charged rod on its axis, where we used integration to derive the final expression. After that, we derived the electric field of a uniformly charged ring along its central axis. An important result is that the electric field at the center of the ring is exactly zero because of symmetry. Finally, we extended the same integration method to a uniformly charged disk and then to an infinite charged sheet. One of the most important formulas to remember is the electric field of an infinite charged sheet. E equals sigma over 2 epsilon 0. Before solving any electric field problem, always identify the type of charge distribution, determine the direction of the electric field, and then choose the appropriate formula. Also, don't forget that symmetry and the integration formulas we learned in this chapter are extremely valuable for solving exam problems. Congratulations on completing Chapter 2. Thank you so much for watching and for supporting the channel. If you enjoyed this course, don't forget to like the video, subscribe to the channel, and share it with your friends. I'll see you in the next chapter. Until then, take care and keep learning.